Okay, so welcome to week four's problem solving session. Today we'll solve week three's assignment as well as week one's assignment, which we couldn't do last time. And then we'll look at an overview of a variance proof of a majority, right? So I also have some questions from week four's content, but um, like all of them are about threshold gates and threshold circuits. And since we're also studying threshold circuits next week, we can solve them next week. Okay, is that fine? Yeah. Okay, so let's start by quickly recalling what we did this week. So this week we saw Boolean circuits for basic arithmetic operations like addition, multiplication, division, and so on. In particular, for addition, we saw three circuits, each one more efficient than the previous one. The first one was the naive circuit, which was a ripple adder. Then we saw a slightly more efficient circuit as far as carries are concerned, called the Carry-Lucas propagator. And then we saw an optimal circuit using the parallel prefix sum idea. And then we also saw circuit for iterative addition. So in the iterative addition problem, instead of just adding two numbers, we are supposed to add m numbers, right? Yeah. And then we also saw a very optimal circuit for this problem. Then we looked at the definitions of some circuit classes. In particular, we looked at the definitions of NCI, ACI, and PCI. So recall that NCI is the class of all circuits of poly size and log n to the I depth, and the fan-in of every gate is at most 2. ACI is similar, the size is poly n, the depth is order log n to the I, but now you allow unbounded fan-in. Okay. And then we also saw the definition of a threshold gate and threshold circuits. So what's the threshold gate? It takes input x1 to xn, and it is 1 if sum over ai xi is greater than equals to some theta and 0 otherwise. Okay. Yeah, so this is what a threshold gate is. And TCI is just like NCI and ACI. It's the class of all circuits. Class of all circuits made solely up of threshold gates, such that the size is poly n and the depth is again order log n to the I. Okay, yeah. And then we saw that addition and multiplication are both in NC1. Addition is fairly straightforward, and multiplication is in NC1 thanks to the circuit for iterative addition. And we also saw that division is in NC2, and we'll see more about division next week. Okay, so yeah. Now let's look at this year's week three assignment. I think the first few questions are just recall questions, so we should be able to do them quickly. Uh, yeah. Okay, the first question is, what is the basis for which Subotovskaya's theorem is defined? B2, De Morgan's basis, and not. So which of these is correct? Okay, so Subotovskaya's theorem works. It has no like restriction on the basis uh, like some other theorems, right? It works for like yeah. Oh wait, no. Okay, so Subotovskaya's theorem has a restriction. It works for De Morgan's basis. Nachipurov's work for B2. Yeah, right. So it's the okay. And okay, so should I ask that question now or later? Okay, yeah, okay. I have one question about this, but I'll ask it later. Yeah, okay. So the next problem is that f p from 0, comma 1 to the n to 0, comma 1, then according to Subotovskaya's theorem, uh, over the De Morgan's basis, the expected value of L f sigma over all sigma selected uniformly at random from Rn Epsilon is upper bounded by which of these quantities? Epsilon square LF plus 1 over 3, epsilon LF plus 1 over 3, epsilon to the 1.5 LF plus 1 over 3, and epsilon square LF plus 1 over 5. So which of these is correct? Yeah, it's C. So epsilon L plus 1 over 3 is simple, right? It's just a counting argument. So, but Subatovskaya theorem improves upon it and makes it epsilon to the 1.5. Okay. And it's this 1.5 that helps us in getting, say, the n to the 2.5 lower bound for Andrew's function. So the next problem is, what is the upper bound for the leaf size of Andrew function on 2n bits over the De Morgan's basis that can be obtained from Subatovskaya's theorem? N to the 2.5 minus O1, n to the 1.5 minus O1, n to n square minus O1, and n to the 1 minus O1. So which of these is correct? Yeah. Okay, just to ensure that all of us are on the same page. So what does 2.5 minus O1 mean? Okay, so let me ask this. Is n to the 2.5 over log n n to the 2.5 minus O1? Is this correct or no? Okay, why is it not correct?
Well, the like power you're reducing is a function of like n, and like you can write the RHS as n to the power 2 by 5 upon n to the power O of 1, right?
Wait, okay, RHS. Okay, so
The thing you just wrote it went away.
right.
Okay. You can you can write n to the power 2.5 minus O of 1 as n to the power 2.5 upon n to the power O of 1, right?
Yes.
Yes. So in denominator I have like n to the some constant.
Okay, so what is O1? Small o of 1. Is it a constant?
A constant. Yes.
It's a sub-constant. Okay, so yeah, that's what I was asking. So, okay, okay, let me write it. So, G of n, small o,
So it means like it is a strictly less than some constant. Does it mean that?
yeah, strictly less than every constant.
Huh.
Yeah, so Gn is small o of Fn if for all c greater than 0, there exists n such that for all n greater than equals to n0, uh, G of n is less than equals to c times f of. So the difference between small o and capital O is this. For small o, you would have for all over here, and for capital O, you would have there exists over here. Okay. So for example, f of n over 2 is capital O of f of n, but f of n over 2 is not small o of f of n. Okay. Yeah. So, so 2.5 minus small o of 1 means the following. Fix any epsilon you want. Okay. Any small epsilon you want. Uh, your function would be smaller than n to the 2.5 minus epsilon for all epsilon greater than equals to 0. But this epsilon has to be a constant. Okay. So is this fine? Basically, what this says is that n to the 2.49999999 is also 5. Okay, you can get arbitrarily close to 2.5, but you cannot get to 2.5. Okay, yeah. Okay, so then let's look at the fourth problem. So the fourth problem is which of the following is true for a formula of smallest possible leaf size over the De Morgan's basis for a function f on n variables x1, x2 to xn. Any leaf xi must have a sibling whose subtree contains xi. Any leaf xi cannot have a sibling whose subtree contains xi. Any leaf xi cannot have a sibling whose subtree does not contain xi. And any leaf xi must have a sibling whose subtree does not contain xi. So which of these is correct? Yeah, it's B. Okay, and so we saw this a proof of this in class, but like this is a very short proof. So can you quickly recall what the proof was?
So basically, we look at the like since it's De Morgan basis, so it's
Right,
like we look at the case of the and we look at the case of the or. So if like we check for like if xi is say 1 or 0, so we find out that the if we put xi to be 1, so the left part is irrelevant. So you can like
right,
the xi in the right subtree is 1, and if the xi is 0, so like what happens is like you can without any consideration put the xi in this subtree as 1 if the gate is and
right.
above it,
Yes,
right? Similar argument for like or you can put there 0, and it works in
right.
every case.
Okay, and does this only work over De Morgan's basis or over other bases as well?
Well, it would depend like if the functions are such that it
Okay, what about B2?
well, we would have to look over the like functions, right?
Yeah, so okay,
uh,
can you think of any function in B2? So just on two variables for which this won't work?
say parity.
Right, yeah. Why?
Yeah. Well,
So,
because the like output depends on both of the uh, you know well, since like the bit is in the subtree, right? So
hmm,
since parity is not monotone, I think like monotonicity would resolve this.
okay,
So the argument used here is like suppose xi is 0, and if it's AND gate, so the output is 0 irrelevant what you like whatever is the value of xi is in the right subtree.
right,
And for xi, like if it's an AND gate and xi is set to 1, so you can ignore the left the leaf, and the subtree containing xi would like you can replace that leaf with 1, right?
right.
So if the functions in B2 like have such results, like you can like fix a particular value in the for xi in the subtree, then I think they should work.
Yes. So, yeah, okay, so if you can say something like this, let's say you have a function f, and if one of its values, okay, if for either 0 or 1, one of its values being 0 or 1 implies that you don't need to correct the other value, then the argument would work, right?
Yes.
Right. So now can you think of a function for which this is not true? Yes, so for example, parity depends on both of its inputs, right?
Right.
So something like this shouldn't be true for parity. Okay. So can you okay, so okay, I'll quickly write down the proof, and in the meantime, can you try to construct an example where the gate is parity and you need xi in both subtrees. So one of its input is xi, you need xi in the other subtree as well. Okay. Yeah.
Okay, I'll have to look it afterwards. Like I can't do it at the moment. Sorry,
Okay.
I'm outdoors, so,
Oh, okay. Yeah.
I might be
Okay.
leaving
So
the lecture soon, but still I'll try.
Okay, so let's quickly write this. So for AND gate, it's suppose you have xi over here, you can replace. Oh wait, you can replace xi with 1 without changing the output. So you can just assume that it's 1 over here, and similarly for OR, yeah, so this is not true. Yeah, just consider the XNOR function. Yeah, so we have this XNOR function, and I want to construct an example where the above fails, right? So uh, consider this. You have an XNOR at the top. You have X over here. Oh, wait, no. What I want in this circuit is okay. So if this is one, the other. Okay, let me try and see what happens if I do it like this. Oh, wait, no. If both are zero, then this is one and this is zero. I think this is the same function. They are unequal, so this is zero and this is one. They are unequal, but these are equal. So this is one and x is zero, so they are unequal, so this is zero, right? They're unequal, so this is zero, which is the same as x, so this is one. And oh yeah, we heard they are unequal, so this is zero, but x is one, so this is zero. They are equal, So yeah, these two are equal. So this is the 1, which is the same as x. So this is 1. Okay, so now if I try to replace x by 0 over here, what do I get? Hmm. X, y. Oh, wait. Why am I putting next one over here? It should be 0. Yeah. So 0 and y are the same. So this is 1. So x and 1, this is 0. This is fine. So y, these are unequal. So this is going to be 1. So y is 1. This is 0. These are unequal. So this is going to be 0. Wait, what did I do? Okay, so y and 0 are the same. So over here it's 1, which is not the same. Okay, yeah. So this is 0. This was fine. Uh, so y is 1. This is 0. So this is 0, which is the same. Y is 0. This is 0. So this is 1. Both are same. So it's 1. And y and 0 are unequal. So this is 0. This is 1. So this is 0. So it gives you a different function. And so for, oh, this is just, wait, it's not a buffer function. Okay. Okay, so y and 1 are unequal. So this is 0, which means this is 1. Yeah, and it just from here it differs from the first function. But yeah, let me just do everything else. So 1, 1, 1, 0, 0, 1, 0, 1, so 0, 1, 1, 1, 1. Yeah. Yeah, so for the x naught function, if I were, in this specific example, if I were to replace x with either 1 or 0 in the subtree, then the function value changes, right? So at least I cannot use the trick that I use for AND and OR gates over here. And so there is at least one example where things can go wrong. Now, instead of y, you can have something very large over here, right? Yeah, so this statement, this statement is not true for every function in B2. And this is the reason why Subatov's-Kaya's theorems proof only works for De Morgan's basis. Because this fact is crucially used in the proof. Right. I'll be applying a random restriction. Yeah, so this is the reason why this proof by Subatov's-Kaya's theorem only works over a De Morgan's base. Okay, let me put it like this. This is the only reason why the proof of the Subatov's-Kaya's theorem does not work over an arbitrary basis. It only works over a De Morgan's basis. Okay, yeah, yeah. So, but however, even then, using Subatov's-Kaya's theorem, you can still obtain a lower bound for B2 because of the following reason. Suppose you have a circle. Okay, should I write it? Okay, let me write it down. It would be easier. Some functions in B2. However, this does not mean that we cannot. Oh wait, yeah, okay. Let me not say this. Yeah, because it gets complicated. You need to worry about these things. Yeah. So it's because of this this property that Subutovskaya theorem doesn't directly say anything over B2. Yeah. Okay. So the if this is fine, we can move on to the next problem. Okay. So then let's look at the next problem. So the next problem is which among the following is the best upper bound for the leaf size of a formula for the Andrew function over De Morgan's basis? The options are n, n square, n cube, and n to the 4. So which of these is correct? Okay, so it's n cube. And before we solve this, like we'll need two problems from homework one to solve this. So let's go and first solve those problems. Oh yes, this. So the first thing that we'll need is what is the optimal and or and not circuit size for the parity function on two inputs. And the options are 3, 4, 5, and 6. So which of these is correct?
I think 4.
Yeah, it's 4. Okay, so what's the parity? So it's x, y, 0, 0, 0. Okay, so one way to try to construct this is put an OR gate at the top and two AND gates. And then I need not x or y and x or not y. So what's the size? One, 2, 3, 4, 5. So this is size 5. Okay. So, but can we do better? Okay. So over here, we use the or of and representation, right? So this is a DNF,
Yeah.
right? Yeah. So what we can try to do is uh, draw CNF for this. Okay. So in the CNF, you will have an AND gate at the top, and okay, let me make this a little wider. It gets congested. Yeah. Okay. And so it's OR of two things, and I'm supposed to do an AND over here. Oh, wait, I thought you do the same thing. It's AND of ORs. Okay, so this is okay. I want it to be 1 when x is 0. Well, okay, now I have to take this in terms of OR. So I want it to be 1 when either both of the okay, I want it to be 1 when exactly one of x and y is 1, right? So, okay, so okay, I want it to be one when exactly one of x and y is one. So when I put x and y like this for it, under an OR gate, this would be one when at least one of them is one, right? So either one is one or both is one. So now I need to rule out the case where both are one, and the way to do that is okay. So when is this gate one? At least one of the x or y is one, and when is this gate one? When okay, so this gate is zero when both of them are one, right? So this means greater than equals to one. Okay, so this means x. Okay, uh, at least one of x comma y is one, and this means that at most one of x comma y is one. Why? Because if both are one, then it would be zero, right? So combined, these tell us that the circuit would be one only when exactly one of x and y is one, and that is exactly parity, right? But the size over here is still 5. One, yeah. Okay, so we have tried a CNF, we have tried a DNF, both give us 5. So how do we get to 4?
Have any idea?
Oh, your voice broke. Can you repeat it?
Oh, I mean, I don't have any idea how to go to 4.
Okay, so the way to get to 4, so is okay, so there are, okay, first of all, these three gates are going to be necessary, right? So you want to write,
Yeah.
yeah. So the way to get to 4 would be to say, okay, over here there are two NOT gates. Can I get rid of one of them? And the way to do it is this. So what is this gate? This gate is not X or not Y, right? Now, what do we know about not X or not Y from De Morgan's laws? So what is this equal to?
Oh, De Morgan's theorem. We can.
Yeah, yeah. So from De Morgan's theorem, this is equals to not X and Y, right? So I can convert this circuit to this and or not and X, Y. What did I do? It's not. Yeah, so these two are the same circuit, right? Because this is not X or not Y, and this is not of X and Y. So this has size 4. Okay, and in fact, this is a formula, right? Because the underlying graph is a tree. So the circuit is a formula. So yeah, so the circuit of size gate, circuit with 4 gates that we get is a formula. And this we'll use in the next problem. And where is that? Okay, yes, it's this. So pick the smallest upper bound on the size of a De Morgan formula computing parity on n inputs. The options are order n cube, order 2 to the n, order n square, and order n. So which of these are correct? Which of this is correct?
I think n square.
Yeah, it's n square. Okay, so and why is this true? So like how do you go to how can we prove this?
Using Kravchenko's theorem.
So Kharchenko gives you a lower bound, right? Here it's an upper bound. So Kharchenko tells you that every circuit computing parity must have size at least at least order n square, right? Over here, what you
Yes.
want is formula. Sorry, Kharchenko tells you that every formula computing parity has size at least omega n square, and over here you want a formula of size at most omega n square, right? Order n square. So here
Yes.
you don't have to use Kharchenko's theorem. Here, what you have to do is uh, construct an explicit formula which computes parity and has size order n square. Okay, yeah. So how do we do this? Okay, so first let's do something simple. Uh, okay, so what we'll do is we'll first construct a formula for parity over V2. So any function over two variables is allowed. Okay, so how can we? What's one way to do this? Okay, so one way to do it is this. N over two. Yeah, so parity on x1 to xn is the XOR of parity on the first half of the bits and the next half of the bits. So is this clear why this is true? Should I explain?
Please explain.
Okay, yeah. Okay, so when is parity x1 to xn 1?
Odd number of ones.
Right. So if and only if the number of x cells that are 1 is odd. Okay. Okay, so now there are two cases, right? Okay, so let ni be the number of x cells Okay, I should write xj's. Okay, let me write nb over here. Or rather, let me do it like this. Yeah. N1 is the number of x's that are 1 when and N2 is the number of x's that are 1 for in n over 2 plus 1 to n. Okay, so we want to find out whether the number of xi's are 1 or is odd or not. And what I'm doing is I'm looking at the number of xi's in the first half of the string and the number of xi's in the second half of the string, right? Now, so I can say this, right? Parity. So is this fine?
Yes.
Yeah. Okay, so when is n1 plus n2 odd? Okay, let me draw a table that will be much easier. So there are two options for each of n1 and n2, right? Odd. Okay, so when both are odd, n1 plus n2 is even, right?
Yes.
When one is odd, it's odd. And when both are even, it's also even, right?
Yes.
Right. So this already looks like the truth table of parity, right?
Yeah.
Uh, and to make this formal, you can do it like this. Yeah, I don't have any. Yeah, this looks okay. Let me move this to the next page. Okay, so what we want to do is from this table, we want to construct this table, right? So when n1 and n2 both are odd, uh, I wrote odd and even in. Okay, I'll have to redraw this. Okay, so when n1 is odd, the first parity is odd, is 1, right? Similarly, when n2 is odd, the second parity is odd, right? Second parity
Yeah.
is 1. And so the parity would be 0, right? Overall
Yes.
parity, because that's n1 plus n2. Similarly, it's odd, so 1, even, so 0, and odd, so 1, right? Even, so 0, 1, 1 and 0, 0, 0, right? So this is just a truth table. So if this were y1, this were y2, this is just y1 XOR y2, right?
Yes.
Yeah. And so if we, yeah, so that's exactly what I've written over here, right? Parity, XOR parity.
Yeah.
Yeah. So this is fine, right?
Yes.
Yeah. Okay. So we have this recursive relation, right? And using this, we want to construct a formula for parity over B2. So this is very simple, right? The formula just looks like this. You have XOR. So you, at the top, you have XOR. Over here, you want to compute parity. Over here, you want to compute parity again, right? So
Yes.
basically, it's going to be a tree of XORs. And at the very end, you would have X1, X2, up to Xn, right? So this is a circle for parity in. So is this fine?
Yes.
Yeah. And what's the size of the circuit going to be?
Uh,
Okay, so what's the depth first?
be log n. Yeah.
Yes, yeah. So there are, this is the complete binary tree with n leaves.
Yeah.
So depth is log n, right? And so what's the size?
Uh, 2 to
So if
the
the
power log n.
minus one.
Yeah, 2 to the power log n minus n minus.
So it's n minus one, which is order n, right? We don't care about minus one that much. It's order n.
Yeah. Yeah.
Okay. So over B2, we get order n. But the question is, okay, what is the size of parity on n inputs over the De Morgan basis, right?
Yeah.
Okay. So now instead of formula, if I had a circuit, then I could have gotten a circuit of size order n. Why? Because I know a small rate about each and every of this parity, right? Or and and one not x y, another not y x, right? So for each and every of each of these parities, I know a small circuit, right, which I can plug over
Yes.
here,
Yes.
and this would give me a circuit of size order n over the De Morgan's basis, right?
Yes.
But what I want is a formula, and the issue is the following. So when I draw this gate is my x, right, and this gate is y.
Yeah.
Okay. So and oh, okay. Let let me copy the formula from there. Okay, so we have this formula, right? Okay, let me attempt one. Write this circuit. And instead of x, y, now what would I have? I would have input one, input two, right?
Yes.
Okay, so now let's look at this parity. This is input one. Ah, this is input one, and this is input two, right? Okay, so now the issue is this. Look, I'm using input one twice, right, in this circuit over
Yes.
here. So what I would have to reuse this gate twice. So The fan out of this gate would be 2, right?
Yes.
But that's not allowed in the formula, right? So in formula, the fan out of every gate must be 1.
Yes.
So you see the issue, right? We cannot directly replace this.
Okay.
So is the issue clear?
Yeah.
Yeah. So what we'll have to do is this. Okay, let me do it like this. Okay, let me first write and then I can explain. Yeah, so, so replace each XOR with this, and so now what we'll do is we'll replace this gate, but we'll have two copies of these entire subtrees. So there will be two copies of this, there will be two copies of this. That would solve the issue, right? Because one copy can go over here, one copy can go over here.
Yes.
Yeah. Okay, so this is what we are going to do. And so now what will the size be? Okay. So so okay, so let me just write one step of this. So parity n will look like or not of the copy. Right. So it's going to look like this. Okay. I've just written down this circuit very explicitly for the topmost gate. So now what's the size of this? So the size of this is one additional gate, two additional gate, three additional gate, four additional gates, plus four smaller parities, right? So if so what I want to do now is write the size of parity n as a recursive relation in terms of size of parity n over 2. So what would the recursive relation be?
So Sn is equal to 4 Sn by 2 plus 4.
Right. And what is the like when you solve this, what do you get? Okay, so let's try to solve this. So it's 4 Sn over 2. So now I get 4 square Sn over 4 plus 4 square plus 4, right? So I just replaced Sn over 2 by 4 times Sn over 4 plus 4. So this is what I get, right?
Yes, yes.
Yeah. Then what about the next would be 4 cube Sn over 8
A Yeah. 4 cube, 4 square, 4 5. 4.
So at the very end, so this would be 4 to the, okay, so in the denominator, so when this becomes 1, it's constant, right? The size is
Yes.
constant.
Mm.
So over here you have 2 to the I. Okay, let me write one more step. That would make it clearer. Yeah, so okay, I'm running out of space, so let me do it over here. So this would be 4 to the I S n over 2 to the I plus 4 plus 4 squared plus 4 cube up to 4 to the I, right?
4 to the I. Yes.
Yeah. And we would be done when I equals log n, right?
Yeah.
So this is 4 to the log n times some constant. It's 1. So in fact, yeah, the constant is just 1. The parity of 1 is just 1, right? You just output the variable itself.
Yeah.
Plus 4 plus 4 square plus 4 to the log n, right? And okay, let me, yeah. Okay, so, and what is this? So this would be something like constant times 4 to the log n
And
plus 1, right?
yeah.
Okay, so I need to move this somewhere. Okay, and what is this? This is constant times 2 to the, okay, I can replace this by 4 times constant times 2 to the log n square, right? Is this fine? So I took this 4 out and I wrote 4 as 2 to the 2 log n, which is 2 to the log n square.
Yes.
Yeah. And what is this? This is just some constant times n square, right?
Yes.
Yeah, so this is order n square.
Yeah.
Yeah, so that's the answer. Is this fine?
I have a question.
Yeah,
So if we replace the XORs, the tree of XORs, by a formula of XOR, it would still result in a formula.
it would result in a circuit. So that was our first attempt, right? So over there, so this is the formula,
Uh,
right?
uh-huh.
And so our first attempt was replace every XOR by this formula.
Yeah.
Okay. But now what is the issue? So this is input 1 and this is input 2, right? Now, even though this thing is a formula, it's using input 1 twice and input 2 twice, right?
Yes.
So when you replace, so suppose uh, you had, uh, so what you would have done is you would have two formulas for these, right? And that those formulas would feed in over here, right? So
Yes.
basically, when you do this replacement, this gate would have been replaced by something, right? So you
Mhm.
would have two formulas, one for IP1 and one for IP2, right? But now when you replace, now to make this circuit, what will you have to do? You'll have to plug in this IP1 at two places, right? And IP2 are also
Mm.
at two places.
Yes. Yes.
So even though this thing is a formula, the resulting circuit is no longer a formula because in that circuit you have two gates, one for IP1, one for IP2, and they are now being used twice in the overall circuit, right?
Yes.
Yeah, so just let's say you have a formula in one basis and you replace every gate, sorry, you do replace every gate by its equivalent De Morgan formula. You need not get a De Morgan formula, right? You might get a De Morgan circuit.
Okay.
unless you
Actually, that's
replicate the
only I want.
index.
Okay.
Yeah. So over
Yeah.
here, what Fix did was replacing every formula, so replacing every XOR gate by its formula and replicating, right?
Yes.
Yeah. So is this fine?
Yeah.
Yeah. Okay. So now going back to where we started from. So recall that we wanted to construct a formula for Andreev's function, and
Yes.
for that we constructed these two formulas, right? The reason was in Andreev's function you have XOR, right?
Yes.
Yeah. So that's why we constructed a formula for parity. Parity and XOR are the same, right? So parity on x1 to xn is just x1, XOR x2, XOR x3, and so on, right?
Yeah.
It follows from this. So if this is XOR of x1 to xn equal to this is XOR of these numbers, these bits, then combining with this central XOR, you get XOR of everything, right?
Yes.
Okay. So now let's go back to that Andrews function. Okay. So the question is, which of the following is the best upper bound for the leaf size of a formula for Andrews function on De Morgan basis, right? So first, let's recall Andrews function. Okay, suppose let me describe this intuitively, and then I'll write it a little more formally. So what we are
Yeah.
doing is, yeah, we are taking,
Actually, Andrew function, we divide the string into log log
yes,
n by 2 bits. Sorry, I don't remember. I think n log n rows are there,
right,
and the column size is
and log n over log n, right? Because log n times n.
n over yeah.
Yeah,
And then we XOR each of those bits in each of those rows, and uh, that string uh, is
right. So what you do is you have log n many blocks, right? You
yes,
compute
yes,
XOR of every block. That would give you a string
yes,
of size log n, and you use that string to index into y. So y is a string of length n, right? So you can index any element of y using log n bits,
exactly, yes, yes.
right? So you use the log n, the XOR that you computed, the log n size string to index into y.
Could you please give me a little intuition? I'm actually very confused. First of all, why do we XOR and then get a string and then use that string as an index to another string? I mean, it is a very strange type of definition.
Right. So okay. Uh, okay. So for now, forget about XOR. Okay. So somehow, for now, let's suppose that somehow you got a login size string out of X, and you are using this to index into Y, right?
Yes, yes,
So now what you can think of this is the following. Y is a string of length n. So Y can be thought of as a truth table of a Boolean function or log n many bits, right?
hmm,
And by indexing, what you are doing is you are just saying, okay, I want this value from the truth table. So basically, you have a function and you are dynamically picking whichever value of the function that you want.
okay, okay.
So think of having a function in the RAM and you are like picking whichever value you want.
Hmm.
Okay. And the reason for XORing comes from the fact that if you don't, okay, so why did we think of Andrews function to prove a lower bound, right? Using
Yeah,
Sobotov's theorem.
yes,
And over there, we are randomly restricting things, right?
yes,
And what we want is after the random restriction, the resulting formula should have large size. Sorry, resulting function should have a large formula size, right?
yes,
In that case, we get a better lower bound.
yes,
Now, observe that XOR behaves very well under random restrictions. So for example, you have uh, log n many blocks, right?
Mm-hmm.
Even if only even if you restrict every variable except one in each and every block, the XOR is still undecided, right? So let's say you have the first block x11 to x1. Uh, okay, so the first block was this, right? X11 to x1 log n over log n.
Yes.
Suppose you restricted every bit except x11, right?
Yes.
Now, depending on the value of x11, XOR can still be 0 or 1,
Yeah.
right? So
Yes.
even after you restrict everything except one, XOR is still undetermined.
Yes.
And this would imply that even after this restriction, the function value, the resulting function must have a large formula size, right?
Okay.
Because what's the
Yeah.
size you require? You require the size to compute the entire function y, right?
Yes. Yes. Yes.
Right. So this is why you use XOR. For example, if you had used and, this would not have worked. Because even if you put one of x11 to x1 over x1 n over log n to 0, you are done. Function is decided,
Uh-huh.
right?
Okay.
Yeah. So
Yeah.
the reason for so your question was this, right? Why use XOR? Why index? Okay.
Yeah.
So first I answered the question why index. It's basically saying you have this function in your memory. You are picking one thing at random. Sorry, not at random, but one of them as you want, right? One value as you want.
Yeah. Yes.
And
Yes.
why
Yes.
use XOR? To ensure that it behaves very well in the random restrictions.
Okay. Yeah.
Yeah. So you can think of this as a sort of a composition of functions, right? You have this function y, and you
Mm-hmm.
are sort of composing it with this x and uh, picking things as you want.
Yes.
So there are two functions over here: unreduced function and y,
Yeah.
right? Okay. So now to solve this problem, I have to write unreduced function a little more formally, and that is messy. So if you don't understand anything I write, just stop me and ask me at that point because yeah, it's a little messy.
Yeah. Sure.
Yeah. Is yj where j is j0 plus 2 times j1 plus 2 square times j2 plus j. Okay, you know what? Let me not go from 0. Let me go from 1. Yeah, so basically this is just the binary representation of. So let me use this notation, the binary representation. This is just going to be j log n all the way down to j. Yeah, so what I'm saying is this is going to be yj, where j's binary representation is this string, and now I have to tell you how I have obtained this string, right? So far what I said is I have indexed into y, right?
Yes.
So now I have to tell you how I am indexing. So how I'm finding this index string, j log n to j1. And for that, divide So I'm going to call them. Okay, to make things simpler, let me just call this number. So I'm calling n over log n m to make my tasks. Okay, let me know. Create some space. Okay, so I've divided uh, x into log n many blocks. And then what I'm going to do is I'm going to XOR them. And okay, this is going to be J1. This is going to be J2. And this is going to be J log n. Okay, so I had indexed into Y. Now I'm telling you how I'm computing the index string, right? This is exactly what we described, right? This is the formal way of
Yes.
writing what we described, right? So is this fine?
Yes. Yes. Yeah.
Okay. Okay, so this is the definition of armtree function. Now, what should our strategy be to compute it? Like, can you propose a strategy? Okay, so we are doing two things, right?
Uh,
Yeah,
oh, I mean, I can see only XOR functions.
right. Okay, so we are doing two things, right? Computing the index string and then indexing, right?
Yes.
Okay, so the strategy should be simple, right? First compute the index string, then index. That's it. So
Yes.
construct, divide. Okay, so our task is to construct a formula, divide it into two tasks. First, a formula to compute all of these, and then a formula to index, right?
Yes.
Yes, so the strategy is this. Hmm, okay, let me write these in bullet points. So let me call this one and task two is use to pick yj, right? So is this fine?
Yes.
So let's complete. Let's assume that we have somehow done task one, and let's just see how to do task two first. Okay. Okay. So what I'm going to do is the following: for all I in n, we will have a gate. Okay, so do you remember the multiplexer circuit from digital electronics or CU or some other class like that?
Sorry, I don't remember that.
Okay, so a multiplexer circuit does basically this, right? Uh, you have n many things, and you want to pick one of them using log n, a string of size log n, right? So what we have to do is construct exactly the multiplexer circuit. So it's fine if you don't remember it, I'll show the construction. Okay, so for all I in n, we will have a gate gi. Okay, so what we are to accomplish task two, what we are going to do is we are going to have uh, ENF. So it's going to be an OR of n's, and it's in fact going to be an OR of GIs. Okay, so what does a gate GI do? It outputs not one. What am I doing? It outputs YI if and only if J equals I. Okay, so J is our index string, right? We
Yes.
have a gate which out. So now we have many gates like Y1 to Yn, and when our index string is J, we are going to pick sort of the Jth element of it, right? And if
Yeah.
we OR all of this, we get our Andrews function, right?
Yes.
Yeah. So now okay, then Andrews. I'm not writing things in the bracket. Yeah, so this is Andrews function, right? So now we have to somehow show how to construct GIs. Okay, so here's the way to construct GI. So GI is just going to be this. It's going to be the end of YI and this thing. So this thing is only one when I and J are the same, right? So the output of GI is going to be YI if and only if uh, GI is 1 and 0 otherwise, right? We should write it 0 otherwise. So this is a GI, right? But now I need to show you how to implement these, right? So is this formula for
Yes.
GI fine?
Yeah.
Okay. So okay, no, no, no. What am I doing? Okay, so over here, okay, so let me say this. Right? So I0 is equals to J0 is the knot of I0 XOR J0. Okay. Why? Because I0 XOR J0 is 1 if and only if both are different, right? So the knot of it
Yes.
would be 1 if and only if both are same.
Yes.
So This is one way to do it, but it's a better way. So over here, I0 is not a variable, right? It's a fixed constant
Yeah.
because we are going from 1 to n. So yeah, for example, for when we are at 1, I0 would be all zeros and so on, right? Actually, I should index y from 0. Yeah, it's better to index y from 0. So I'm indexing y from 0 because like I have a string of length n, right? Log n, and that goes from 0 to n minus 1. So it's much easier if I index y from 0, right? It's much easier to pick if I index y from 0.
Yes.
Yeah. So then I should change this over here. Yeah, now it's fine. Okay, so for example, let's say we are constructing G0, right? Then all of these I0 to IN are going to be 0, right?
Yes.
Similarly, whenever we are constructing GI, I0 to IN are fixed, right? So what you can do is and of, let me write it like this, and uh, J0 or J0 complement. Okay, let me do it like this. I want to be equal, yes, so I want them to be equal, yeah. Okay, so what we are going to do is the following. We have fixed I, so we have fixed I0 to I log n, right? Now, if I0 is 0, we are going to replace this thing by not J0. And if I0 is 1, we are going to replace this thing with J0. Okay, now why does this work? So when is not J0 0? Sorry, when is not J0 1? Only if J0 is 0, right? So only if J0 and I0 are the same. Similarly, when is J0 1? When it's 1, and so I1, I0 and J0 are the same, right? So these two are equivalent. Is this
Yes.
fine? Yeah.
Yeah.
And the reason we did this was now we are only, so remember, you want to consider a formula, right? So over here we are using each and every one of J's, oh wait, there is, oh, J starts from 1, right? Why am I putting 0 over here? So the indexing of J starts from 1, right? Over here. So I should put 1 over here. Yeah, yes, sorry about this. Okay, so now recall that we want to consider a formula. And so, suppose we had replaced this by not of an XOR gate, right? Then every XOR gate over here would use J1 twice, right? And so we would have to replicate the circuit that computes J1 twice, and that would blow up our formula size, right?
Yes.
Now over here, J1 to J log n are used exactly once. So per GI, you need to compute them only once. You don't need to compute them twice, right?
Yes.
Yeah. So this is GI, okay. And AN is going to be all of GIs. But so far I've just completed task 2, right? I need to complete task 1 as well, right? So task 1, and this is the reason I did task 1 after task 2. So we want a formula, right? So for every GI, so every GI is using J0 to J log n. So for every GI, I must compute J1 to J log n once, right? So since there are n many GIs, I need to have n many copies of J1 to J log n, right? Because I want a formula,
Yes.
right? So per GI, okay, so there are J1 to J log n are just XORs, right? So yeah, so we call that J1 to J log n are just XORs.
Yes.
And how many of them are there? There are log n many of them, right? So what would be the cost? The cost would be log n times the formula, size of the formula to compute one XOR, right? So the cost would be a log n times order n square over log n. Why? So because we saw in that question in assignment 1 that to compute XOR of n inputs, you need circuit of a formula size n square. So now every one of J1 to J log n is XOR of m equals to n over log n many bits, right? So you need a circuit of size n square, which is n over log n square over log square n, right?
Yes.
Right. So and this is equal to order n square over log n, right?
Yeah.
So to accomplish task 1, per GI we incur order n square over log n cost. Okay, this per GI is important. So now let's look at the size of the circuit, the formula. Okay, so what is, I'm just going to copy this. Yeah, so AN is just the OR of all the GIs, right? This we saw. So, okay. So now there are two components to size, right? Size for every GI, size of every GI, and these OR gates, right? So how many OR gates are there? You need like order n many OR gates, right? So this is an OR
Yes.
gate which span in n. So to make it a fan, so to compute this using just spanning two OR gates, you need a tree of size, like size n minus one in depth log n, right?
Yes. Yes.
Right. So size of an is equal to n times size of, okay, let me do it like this. 0 to n minus 1 plus n minus 1. N minus 1 would be from this OR gate, right? So you have n inputs, you need n minus 1 OR gates. Okay, so this is n times the size of uh, size of G0. Okay, this is less than equals to actually. Okay, so my claim is that this quantity is upper bounded by this. Why? Because if you look at the circuit for GI, for almost every GI, the circuit was the same, almost the same. The only difference is whether you are picking this or this, right? And that's why I picked 0 because for 0, everything is 0. So you need NOT gates, right? Lots of NOT gates. In fact, you need log and many NOT gates, right?
Yes.
Yeah. So size of G0 is the largest among these. So I picked G0. Okay. And okay, so now what size of G0? Okay, so this is what G0 looks like. So it's you need one, you need like log n many AND gates and log n many NOT gates, right? So like, okay, let me just put a less than equals to. So this is for AND gates and NOT gates that I require in this expression. Okay, plus the size required to compute each of the GIs, right? And that we saw is over here, order log square n. So plus order log, sorry, n square over log square. Yeah, so size of, okay, so when I multiply n to this thing, what's the dominating term? It's this, right? So I can write n
Yes.
times order. Yeah, but again, this is a dominating term, so I can ignore the other term, and this is just, and yeah, so this is the circuit you get. Oh, wait. No, 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 it's log n. Yeah, so over here it's order n square over log n. Yeah. So I need to remove these two everywhere. Yeah, so it's log n over here. Yeah, so it's order n cube over log n, right? Because this was log n put log square. Yeah. So is this fine?
Yeah.
Yeah. And yeah, so if you look at the options, the tightest is n cube, right? The closest is n cube.
Yes.
Yeah. So that's among the options, that's the best. So is this fine?
Yeah.
Yeah. Okay, so we still have 20 minutes, so we can solve a few more problems. Yeah, so let's look at the next one. Okay, so the next problem is which among the following functions can be computed using the basis and or. options are parity, majority, both, and none. So which of these is correct?
Majority.
Yes. And what is the reason that majority can be computed but parity cannot be?
Because parity will require those not gates.
Right. So
So
I
I
mean, one
mean,
way to
in majority we can do with monotone
right. Yes.
circuits.
So that's like the exact explanation. So last class we saw this that every monotone function. So we saw this last class in the last problem solving session, and we also know that majority is monotone. So together these two imply that majority can be computed. Okay, so this tells us that majority can be computed. And how can we rule out parity? So one way is like what you suggested, try everything, try the circuits for parity, try every circuit that computes parity, you will find at least one not gate over there. Another simpler way is this. So we also saw last time that okay, and we know that parity is not monotone. And together these two statements imply that so is this fine? Like is it clear why parity is not monotone?
Yes.
Yeah. Yeah, so from these two things that we saw in the last class, we can conclude that majority can be computed and parity cannot be computed. Yeah, so the option is B. Is this fine?
Yes.
Yeah. Now let's look at the next problem. So the next problem
Uh,
is,
could you
yeah.
explain that eighth question first? I mean, the last one. Yeah, this one.
Oh, so I think this is just a recall question. So this will take 1 minute, then we can go to it. Yeah. So according to Valiant's theorem, which among the following is the optimal upper bound or the leaf size of formula for the majority function on n bits over this basis. N to the 2.5, n to the 2.3, n to the 3.5, or n to the 5.3. Yeah, so what we saw in
Yeah,
the class was, yeah, you were saying something?
it's yeah. No, I was saying just for n to the power 5.3, I think.
Yes, yeah. So what was Valiant's theorem? Valiant's theorem was a monotone circuit of size n to the 5.3 for majority, right? But a monotone circuit is exactly a circuit computing using just OR and AND gate. So yeah, this is just another way to state Valiant's theorem, right?
Yes.
Yeah, so now let's look at the next one. Okay, so consider the function f equals x1 parity x2 or x1 xy x2. What is the value of the amplification function f of AFP. P square, P minus P square, 1 minus P square, 2P minus 2P square. Okay, so what is the definition of the amplification function? So what is this? So what is this?
Um, so it chooses assigns a value 1 with probability p and assigns a value 0 with probability 1 minus p. And
To every variable independently, right?
yeah,
Right. And then it just takes the expectation, right? So
yes,
it's this. Oh, so do you know the Bernoulli distribution? Like we
yeah,
write it. Yeah, so Bernoulli P is just a distribution where 0 is picked with probability 1 minus P and 1 with probability P, right? So this is exactly the
yes,
amplification, right? Okay.
yes.
Okay, so
So what exactly this word amplification indicates?
oh, I don't know why we are using the word amplification over here.
Oh,
Yeah. So at least in the proof of variance theorem, it made sense because it's like this quantity which approached majority, right? So this was sort of go. So okay, by using this quantity, so okay, so if you recall variance, the proof of variance theorem, what did we have? We had so for every depth I, sorry, for every depth 2I, we had a complete binary tree of OR and of AND and OR gates, alternating levels,
yes,
and we plugged in like variables and zero with some probability, right?
yes, yes,
So for every depth, we had sort of this random circuit, right?
yes,
And what we showed was this: as the depth increases, the probability that this random circuit starts agreeing with majority becomes larger and larger, right?
yeah,
Right. And so over there, it was this quantity that was helping us, right? So we were sort of amplifying the probability that our circuit computes majority. And like this was amplification because this was increasing level by level, right? So the probability was being amplified. So I think
okay, okay, yeah, yeah,
at least
yes.
for that proof, this makes sense. But I don't know why in general this is called amplification. Not so. For example, why is it called amplification when we are not using it in the context of that proof? Okay, that I don't know.
Mhm. Oh, okay.
Yeah. So in fact, in Valiant's original paper, it does not use the word amplification. Yeah, he just uses the expression directly. Okay, so now what's expectation? So expectation is just this, right? Sum over. Okay, let me write it like this. Oh wait, please forget this. So this is the expectation, right?
Yes.
Yeah. Okay. So now what is this probability? Probability x1 equals 0 and x2 equals 0. So my claim is it's this.
Okay, so later on that F will be replaced by XOR.
Yes. Yeah. So okay. Yeah. I mean, I can. Okay, I can do it over here. So my claim is these two quantities are the same. Why?
Because independently they are.
Right. Yes. So here is where we are using independence, right? Yeah. And I'm not writing the rest. So in like everything, I'll just split this, right? Okay. Let me write it. Yeah, because I want exact. Okay. Now we know these two are zero, right? 0 XOR 0 and 1 XOR 1 are 0, right? So we can
Yes.
completely ignore these two. So we are only left with these two. And so this is 0 plus this is 0. So what's probability x1 equals to 0? That is 1 minus p1.
Yeah.
So this is 2 times 1 minus p times p, which is 2p minus p square. Yeah. So it is fine.
Yeah.
Oh wait, 2p minus
Ac-
2p square. Yeah. 2 is
yeah.
multiplied with again. So
Actually, I
it's
was trying to do by constructing that XOR tree, which we
oh, okay.
constructed earlier, and then assigning the probabilities. So I was getting, I was not getting anything
Yeah.
meaningful.
I mean, you can directly get this from the definition, right? Let's just expand this out.
Mhm.
Yeah.
I have one question. I'm actually always confused about this random restriction and this partial assignment. So,
Okay.
could you give me a very small example where I can see the difference?
Oh, okay, that's pretty simple. Okay, so okay, what's the difference between a partial assignment and a random restriction? So a partial assignment is just a partial assignment. So you have x1 to xn, you replace some of them. So what an assignment of x1 to xn? You replace every one of x1 to xn by some values, right? Say b1 to bn. Okay, that is an assignment of x1 to xn, right? Hello, can you hear me? Hello.
Yes, yes, yes.
Yeah, okay. So what I was saying is, what is an assignment of x1 to xn? You take x1 to xn, replace them by some values b1 to bn, where b1 is 0, 1, b2 is 0, 1, and so on, right? So
Yeah.
this is an assignment of x1 to xn. Okay. So what does the partial assignment mean? You don't replace every one of x1 to xn by some values. You replace only some of them. Okay.
Yeah.
Right. So let's say you have x1, x2 up to xn. You replace
Okay.
x1, x2, x3 up to xn over 2, right?
Yeah.
By b1, b2 up to bn over 2. This
Mhm.
is a partial assignment.
Okay.
Okay. Now, what is a random restriction? So it depends on how you want to define it. So one way to define a random restriction is this. Uh, Pick a subset of x1 to xn. What? Okay. and assign the variables in this subset to random values. So a random restriction is a subset of x1 to xn along with a partial assignment of x1 of that subset, which is random. Okay. So for
Mhm.
example, if the subset was x1 to xn over 2, then a random assignment would assign x1 to xn over 2 random values. So we saw partial assignment, we saw a random restriction. What's the difference between the two? So in the partial assignment, you replace x1 to xn over 2 by some fixed value, right? B0, B1, B1, B2 up to Bn over 2, right?
Uh-huh.
In random restriction, you replace them randomly. So x0 would be 0 with probably something, 1 with probably something, and so on.
Okay, okay.
So basically, random restriction is just a distribution of partial assignments.
Okay.
Right. So for example, let's say I had just x1, x2. A
Uh-huh.
partial assignment would substitute x1 to 0, x2 to 0, x1 to 0, and x1 to 1, right? A
Yes.
partial assignment will do one of these. What would a random restriction
Mm.
do? It would use the first partial assignment with probably half, the second partial assignment with probably half, right?
Okay, okay.
So for a random restriction, you just pick every partial assignment with equal probability. Once you have fixed the
Mhm.
subset that you want to restrict.
Okay.
Yeah. So you can
Mm.
like very at a very high level, random assignment is just a random partial a random restriction is just a random partial assignment.
Yeah.
Yeah.
Yes.
Yeah. Okay, so we still have like 5 or so minutes. So let's quickly look at some more questions from week one assignment, unless you have some questions about week three or week four.
So
Okay, so
I,
yeah, yeah,
I
you were
mean, we
saying?
can look at some question.
Okay, yeah. So the first problem from week one was the number of functions on n inputs is what? 2 to the 2 to the n, n squared, 2 to the n, or 2 to the n plus 1. So which of these is
Oh, yeah.
correct?
2 to the power 2 to the power n.
Right. And why is that true?
Yeah, because each
Yeah.
each input can, I mean, there are 2 to the power n inputs, possible
Right.
inputs, and each input could be assigned to 0 or 1.
Yes, exactly. For all x in 0, comma 1, there are two possibilities. For 0, it will be 0 or 1, right? There are so this is 2 times 2 times 2 to the n many times, right?
Yes.
Which is just 2 to the n. Yeah.
Yes.
Okay, so there is another way to count it. It's very similar, but there is a slight conceptual difference. Okay. So here what we did was use the principle of counting. Another way to do
Mhm.
it would be the following. Observe that every function on n inputs can be represented by a string of size 2 to the n, right?
Every
Give me the truth table,
yes, yes.
right? So every function is uniquely represented by a string of size 2 to the n. And how many
Yes.
strings are there? 2 to the 2 to the n. So that's exactly the number of functions.
Okay.
So
Yeah.
what I wanted to point out over here was the following. Suppose you want to count, you have an object O and you want to
Uh-huh.
count how many objects are there.
Yeah.
Okay, so one way to do it is the following. Find out how many bits do you need to uniquely represent O, and then raise that to the power 2. Because there are those many strings, right?
Mhm. Yeah.
Yeah. So this sometimes comes in handy. This like
Yeah.
alternative view. I mean, it's exactly the same. Okay, so at the heart of both this argument and that argument, what's happening is the same, but sometimes that view helps. Yeah.
Yes.
So this we already saw. Yeah. So the third problem is what is the optimal size of a Fanin 2 De Morgan circuit computing n function on n inputs, n minus 2, n, 2n, and n minus 1. So which of these is correct?
I think n minus one.
Yeah. So, okay, so we know that there exists a circuit of size n minus 1, but why is n minus 1 the best? Yeah, so if we want to say that the optimal size is n minus 1, we need to show two things, right? There exists a circuit of size n minus 1, and there exists no circuit of a smaller size, right?
Yes.
Okay. So first is easy, right? Eh, that tree of ands works. Okay.
Uh-huh.
So what about the second? So one way to argue the second thing is the following. Okay. Let size be s. So there is one output gate. Okay, let me write it like this. Okay, so the size is s, and we are fanning 2, right? Since fanning is 2, at most 2, because you can have not gates and then they would have fanning 1. So since fanning is at most 2, s gates can have at most 2s children, right?
Yes.
However, all of the s gates except the output gate feed into some other gate, right? I.e., they are yeah. So except the output gate, every gate must be a child of some other gate, right? Otherwise, you can just ignore it from the circuit. It doesn't. It you compute it out its output, but its output is not being used anywhere, right?
Yes. Yes.
And okay, so it can be a child of multiple gates, but it has to be child of at least one gate, right? So
Yes.
out of 2s possible children, at least s minus one are other gates, right? And that leaves us with at most s plus one gates, which can be leaves, right? So is this fine? So we had at most
Yes.
2s slots for children, And out of these two S, at least S minus 1 are occupied. So at most S plus 1 are remaining, and these can be used, right?
Yes.
Yeah. And since N depends on all of the inputs, S plus 1 has to be N, right? Okay, has to be at least N because like okay, so S plus 1 has to be at least N. Why? Because you need to read everything once, but you might read something twice, right? So it's at least N.
Yes. Yeah.
And this implies that S is at least N minus 1. And this is exactly what we wanted, right?
Yes.
Yeah.
Exactly.
Yeah. So I think we are out of time. So let's
Mm.
end the session. Yeah.
Mm.
So do
Thank
you have a
you.
question? Yeah, because if you don't
No.
have a question, then we can end. And if you have a question, you can ask me now.
No. I don't
Okay.
have. No.
Yeah.
Yeah. Thank
Okay.
you.
Yeah. Thanks. Bye.
Bye.